Okay, so I think recording has been started. No, not yet. Okay, it is started. Okay, so we start with permutation. You already know the that concept of permutation and combination, right? Okay, so what is the meaning of the permutation? So we know already, still I will define that one. So the number of permutations of n things taken k at a time is, so that's mean you have say a1, a2, a3 up to an. You have this n elements, okay? And what you are doing, you are taking k elements, right? You are doing the permutation of k elements. So then the first one, so first choose you have n options, okay? So it denoted by nk. So that's mean you have n elements and you are taking k, okay? So therefore the first element, if you choose first element, say there is a gap here, this is up to k, k positions. So this first position you have n choices, right? Because a1, a2, an up to anyone can be here. So you have n. And then for the second place, since one number is already taken, so therefore you have remaining n minus 1 choices. So it will be n minus 1. And similarly, the kth one will have n minus k plus 1 choices. And it is denoted by that factorial n. You already know what is a factorial n meaning, divided by factorial n minus k. So in other words, suppose you have 1, 2, 3, and you are saying p32. What is p32? So that's mean you have to fill two places, okay, from these three elements. So you can choose one, and for you have two, you have one, you have three. If you take first two, then you have one. If you first two, then you have three. Then if you choose first three, then you will have one, then three, two. So we have these six choices, right? So that's mean it is 3 into 2. You can see by the formula. So it is 6. Now this is called permutation. You already know this one from your 12 standard, maybe earlier than that as well. So there are uses for the permutations because we will see some problems as well. And in the similar notation, we will define that combination. Now, what is the difference between that permutation and combination? Now, for the combination also, we will choose k elements from n elements, but the order does not matter. So that's mean in the combination that 1, 2 and 2, 1 will be same. So that's mean we will choose k elements as a set. Okay. So we can write here it is the number of subsets of size k of a set of size n. Okay. Is, if you denote by cnk, then it is first pnk. So that's when you fill the elements in this way, and then you can permute since that order does not matter. So therefore you have to divide it by your factorial k. Because you choose that k elements, right? And that order does not matter. So you have to divide by this factorial k. And then that will be factorial n divided by factorial n minus k. Okay, use this that notation in k. And usually it is denoted by n choose k in this way. Or you can use that nck as well. But I prefer this symbol. But you can use that one as well. That does not matter. Okay. So we generally pronounce this as n choose k. And if you write in this way, you can say that nck. That does not matter. So this is a definition that we define that 0 factorial. So that is a meaningless, but we define this is as 1, and we define that n choose minus 1 and say n choose n plus 1 as 0. So that is, it is not coming from the formula, we just define that. And also you can note that nc0 is same as ncn, and that is same as 1. Okay. Now by this formula, so what is the meaning of this n choose k? Now we can define a theorem which is also easy to prove. That is n choose k is same as n minus 1 choose k plus n minus 1 k minus 1. Now can you prove it theoretically? So I think you have already seen the proof of this one, right? Because you use this term during your 12. Do you remember the proof?
Yes, sir. So the combinatorial proof or just like splitting into factorials.
But I think I always prefer the theoretical proof. Now what proof you know? You just use that factorial and then by using that definition only.
Yes, sir.
You can
One
say
this
that
one and
right. So just split into this way and take the sum and then you will get, right? But anyway, you can use by the theory as well. That is by using the definition, not using this term, but by using how to choose a function. So what is the main definition of that? So we will anyway, there are many types of proof this one. So we will prove by using the main definition. So obviously any proof is welcome here. So that does not matter. So consider say n set and n set. N set means you generally mean a set with cardinality n. Okay. Say a1, a2, an. Consider this set. Now what do we mean by nck? So that's mean we have to choose a subset of cardinality k. Or you can say that we have to choose a subset which is also a k set. Okay. Now it has actually two cases. Now if you consider that an, now an and case 2, if you split into these two cases, then we are done. So the k subset the K subset of A does not contain AN and the K subset of A contains AN. Okay, so these are the all two possible cases. Now for this case, now look at case 1. So that's mean since we are choosing a K subset of A such that K that subset does not contain AN, right? So that's mean we choose K subset from this A1, A2 up to AN minus 1, right? So that's mean we are choosing this one. And what about the case 2? So this is sometimes called that inductive kind of proof as well. Okay. Now that K subset already contains AN. Okay. And you have to choose the remaining K minus 1 subset from this. So we choose K minus 1 subset from AN minus 1 and then add AN. Okay. So we are actually done. Why? So in the case 1, we had the choices. We have n minus 1 points, n minus 1 elements, right? And we have to choose that K subset for there. So therefore we have n minus 1 choose K possibilities. And for case 2, we have n minus 1 choose K minus 1 possibilities. So therefore we are done. So therefore we have, if we choose K set from an N set, then we have this plus this possibilities. So we are done. So this is one way you can prove it. Is that fine with everyone? Yes. So there are
Yes,
many
sir.
ways to prove it, right? You know that there are many ways to prove it. So this is one way. Okay. Now we see one problem. Now this is also simple. You already know that. Now given that cardinality of A is M and cardinality of B is N. So when we are writing that Mn, that's mean A and B are finite sets. Okay. Now the question is, how many distinct function is, so you can see that you can define from A to B. Now, can you give me the quick answer of that one? That is very simple. So we are asking how many distinct functions are possible from A to B, where A has m number of elements and B has n number of elements. Yes, I am waiting for your answer.
So n to the power m.
Right. So what we'll do here, since we are not giving any restriction on the function, right? We are not saying it is injective or surjective. Okay. So we are just saying what are the possibilities of all possible wave function. So it can be onto, it cannot be onto, it can be surjective, it cannot be surjective. So that does not matter. Now if we choose A equal to say A1, A2 up to AM, and say B equal to B1, B2, Bn. This. Now what do you mean by a function? So that's mean so f is equivalent to f of A1, f of A2, f of AM. Right? Why f is equivalent to that? Because if we know the values at A1, A2 up to AM, then we know the function. So f is uniquely determined by the f of ai, where I is from 1 to m. Now since we are not imposing any position, so for this we have n choices, right? For this again we have n choices, because two a1 and a2 may be same, f of a1 and f of a2 may be same, and similarly for this one we have n choices. Okay, and why this is n choices? Because f of ai belongs to this set up to Bn. So f of a1 can be b1, f of a1 can be b2, f of a1 can be bn. So it has n choices, it has n choices, it has n choices. So we have total number of function equal to n into n up to n. Sorry, yeah. So this is m times. So this is n to the power m. Now see, be careful about the proof. Sometimes I have seen many people do the mistake. Sometimes they write m to the power n. So this is a common mistake which I have seen. So when I have taken the last course and even some other places as well, I have seen that mistake. Okay, so you have to find that what are the values of f of a1, f of a2. Since both are n choices, so we have total number is m number of n. So therefore, product of m number of n's. Therefore, it is n to the power m. Now, if we modify a little bit, so if we ask that another problem again, this is m, this is n. So that's mean they are finite set. So how many distinct one functions is possible from A to B? Now can you give me a quick answer for this one? So here
So
we needed,
NPM.
right. So here we needed only functions. Now we have one functions. Now she is giving answer that it is that permutation, right? So P, you can say that which the way we have
So
defined
we'll
that
have
P N
two
K.
cases here though. If n is less than m, then we can't say any. Then we can say that there are no distinct one functions. And if it's
Huh,
greater, then it's a permutation.
right. Yeah, that is a clever answer. Good. So we to define actually a distinct one function, we must need that m is less than equal to n. Because if m is bigger than, then we cannot have one function, right? So that is a good one. Fine. So suppose I missed actually. So In the question it is given that also m is less than equal to n. And thank you for the clarification. So what are the proof? Again, now okay, these problems you will find very easy because we have seen this kind of problem before as well. So A1, A2, AM, B equal to say B1, B2, Bn. So it is fine if you don't write A and B in this way. I am writing here because to give more clarification. Now again, F is equivalent to this one, f of A1, f of A2, f of AM, right? But here we have an order of this one. That's mean f of AI is not equal to f of AJ for I not equal to J. And f of AI belongs to that set. B1 into Bn. So therefore, this is an M tuple. That's mean what we are taking. We are just taking this M permutation from n elements. So this is just P n M. Or this is a one notation that n P K as well. Oh, n P M as well. Okay. So this is an one use of the permutation. Now similar way we can ask that how many instead of 1 how many surjective function is possible from A to B and say m is bigger equal to n. You can try that. So how many surjective function is possible from A to B where cardinality of A is m, cardinality of B is n, and m is bigger equal to n. Okay, just try this one. Now there is another problem. Now this type of problem generally you will see in the probability as well. I think you have already seen this kind of problem. Say it is given that an urn so consists of 30 red balls and 70 green balls. So with numbers. With numbers means we are actually mean that balls are the different ball. So they are not identical. So there is some confusion with that identical ball or not. But generally when we say that in this kind of problem, when we say 30 ball, so that's mean there are 30 distinct balls. Now what is the number of ways of getting exactly 9 red balls? So if we take or if we draw 20 balls. Okay, so that's mean this is 30 and this is 70. So you have total 100 balls, 30 are reds and 70 are green. And what you will do, you will choose 20 balls, or you can say that take 20 balls, okay, among these two. So they are mixed. So they are mixed, and you have taken 20 balls. So what are the way? So what is the number of possibilities that you have taken? So there are exactly 9 red balls.
So is all red balls are same or different?
I'm saying that they are different, right? With numbers. That is a problem of the combinatoric. Yeah, combinatorics. That is also simple. You have seen this kind of problem. I think you have seen this kind of problem before as well. So you have 30 red balls with numbers. So that's means say R1, R2, R30 like that. But when we choose that 20 balls and among them 9 are reds, that's mean that order does not matter. That means you can get R1, R2. You can take as a set, right? That order does not matter. So what we are asking that just choose 20 balls so that there will be 9 red balls. So what are the number of ways or number of possibilities of choosing this? Yeah, I expect one quick answer because you have seen this kind of problem. No?
So 30C9 into 70C11 divided by 100C20.
No, there will be no divided that you don't have to divide, but we are not asking the probability.
Okay, you're
We are
asking the
yeah,
ways.
we are asking the what are the way that what is the number of way we are choosing that. What are the all possible way. Okay, so you are dividing by 100 say 20 means you are taking the probability of that. So we are not asking that. Okay. So you are just asking that number because this is not a probability course. We are just interested on taking numbers. Okay. So it is given that so since 9 balls out of 20 are red, so that's mean 11 balls are green. So that's mean we ask that choose 20 balls so that 9 are red and 11 are sorry we can choose a different one and 11 are green. So that's mean so now how many ways we choose 9 balls from 30 balls. So that is 30 choose 9, right? And how many ways we can choose that 11 green balls from the 70 balls since they are different balls. So it is 70 choose 11 and this is the product. So this is the number. So this is the number of getting exactly 9 red balls in a sample of size 20. Is that fine with everyone?
Sir, if we are picking one by one, there should also be 20 factorial multiplied with this. Right.
No, there is so what we are saying, it is not an one by one because right. So what we are choosing just we have see it is just a think as a simple one. You have 30 balls. Okay, so you have 30 balls. There is 30 numbers. Say R1, R2, Rn, R30, and mix up with say G1, G2 in this way. Okay, so what you are taking just 9 ball from this 30. So this is just 30 C90. That's all. So actually we asked that choose what are the ways to choose 9 red balls and 11 green balls. So therefore there are 9 choose 30 choose 9 ways to choose that 9 red balls and 11 choose 30, 70 to choose the 11 green balls from the sample of 70. So therefore it is just a multiplication of that. Right? So it is not a one by one. You have to choose that 20 balls together. So you have a set of size 20. So this is the first of all, and there is no repetition is not allowed. Okay, so just think it is as a simple. So you can add some more condition to make it as a probability or some more interesting. But here we keep it just simple. Just a use of a combinatorial one. Okay, so whenever we have this kind of balls, so many people have lots of doubt. So someone says that these balls are distinct or not, they are identical or not, and we have a order or not. So many people have doubt this kind of. So therefore it is better to read the question very carefully. Okay. So,
Okay.
yeah, just try. There will be lots of problems. This kind of problems are available. So just try this kind of problems and it will be, yeah, that will be fine. Okay. So these are the known fact which you already know. And now we will start the fact which you probably don't know. So first one is a Bell number. So are you familiar with that Bell number? I think no. Know what is a Bell number? So first of all, we define a partition. What is a partition? Now you know that one. Now a partition of a set S is a collection of, remember that, non-empty subsets AI. Okay, such that 1 less than equal to I less than equal to K. Okay, non-empty subset this such that it satisfies two conditions. So first of all is if we take that union of all of these subset, that will be S and they will be mutually disjoint. So AI intersection AJ is empty for I not equal to J. Okay, so this is called a partition. Now what is a Bell number? Now for an n set S, that is set with n element, Bn is the number of partition of S. Okay, so we define, so by convention actually we take B0 equal to 1. Okay, now we can define what is, we can find what is B1, B2, B3. We can calculate all of this. Now, first of all, can you tell me what is B1? Can you quickly tell me what is B1? So B1 means number of partition of a single set, singleton set. So this. So what are the partition of this set? What is the number of partition?
Sir, 1.
Only this. So this is just one. Now what is B2? So that's when you have two set. This two element set. Now can you tell me what are the number of partition of this set?
2.
Right. So B2 equal to 2. Why? So we have two partition. One is only that set. Only that set. And another one is this two. Okay. Now similar way you can calculate what is B3. So you have three element set A, B, C. Now can you tell me what is B3? So there are many possibilities actually. So this is one singleton. So this is one choice. If we take A, B, C, and similarly you can define. So this is another one. A, B, C. Right? And you have, so this is 1 plus 1 plus 1. This is 3 only. And there are many options 2 plus 1. So that is, yeah. So A, C, B, and another one is B, C, and A. So these are the all possible choices, right? Of the partition. So total number is 5. So B1 is 1, B2 is 2, B3 is 5. So in this way you can calculate what is B3, B4, Bn, right? But it has a beautiful relation. Now is this clear, that Bell number? What is a Bell number?
Yes, sir.
Okay. Now the theorem is that Bn plus 1 equal to summation k equal to 0 to n choose k, bk. So now this is the theorem. Now again, it is easy to prove actually. So again, you have to just count. So in combinatorics, we will just count. And remember that there are many problems on permutation combinations, but here in this course, we will not focus on the problems on permutation combinations because there are many maybe difficult problems on permutation combination. You tried, right? Even when you were in your 12th, so you find lots of difficult problems in permutation combination. But here we will not use any trick or something any like that. So here we use just permutation combinatorics. So permutation and combinatorics we use here in this course as a tool. Okay, so we will not read those. For an example, this Bell number. So we need these combinations. Okay. Well, so I have slides, so I think it is better to show this one in terms of slides, then it will save time. Otherwise, I have to write each and everything. So I will send you these slides as well. Yeah, right. Now can you see that screen?
Yes, sir. The slide is visible.
Okay. Now also, right?
Yes, sir.
Okay, good. Now we have to prove this theorem, Bell number. Now what we'll do, and now again we will use just simple calculation and we will use just the definition of Bell number. Now since we need to define that Bn plus 1, so that's when we need a partition of a set which has n plus 1 number of elements, right? So we take that set, n plus 1 number of elements. and say take a partition of this set, say a1, a2, am. So there is no value of this m. Okay, so just take a partition. Okay, just take a partition a1, a2, am for some m we don't know. So we don't use that m. So just take a partition of that set. Now, without loss of generality, you can assume that the n plus 1 element, that element is belongs to any of these partition. We take that partition as a1. Okay, so we assume that without loss of generality, we assume that this n plus 1 belongs to a1. Okay, this we just assume that, and then what will be the cardinality of a1? It cardinality have at least one, right? Say its cardinality is k plus 1, where k is some number between 0 to n, because it has cardinality at least 1. Right. Now, what does it mean? So that's mean that A2, A3 up to AM is a partition of the remaining n minus k sets, remaining sets of n minus k elements. Now this form a partition of the remaining n minus k elements of S, which is S minus A1. Is that fine? Now can you
Yes,
tell me, by using the definition, how many partitions are possible for S minus A1? By using the definition of Bn, how many partitions are possible for the set S minus A1? That is a simple one, right? Even not,
Bn
So
minus
Bn
k.
minus k.
yeah, simple. It is just Bn minus k, because you have S minus A1 has n minus k elements. So therefore, how many partitions are possible? That is the definition of Bell number, right? So therefore, Bn minus k. So Bn minus k partitions of these sets, right? Of these sets. In other words, you can say that Bn minus k is the number of partitions of S whose one part is A1. Okay, and what is A1? A1 is just k plus 1, right? That cardinality of k A1 is k plus 1. Now tell me how many ways we can choose k1. Sorry, A1. What are the possibility of A1? How many ways we choose A1? A1 has k plus 1 number of elements, and one number is n plus 1. So how many ways we can choose A1? Here, whose elements are k plus 1? That is, see, we have chosen, so we will choose k plus 1 elements from n plus 1 elements, but one number is fixed. So therefore, we will choose k elements from the set of 1 to up to n. So therefore, total number is n choose k. Is that fine? The total number is n choose k.
yes, sir.
Fine. So therefore, can say that the total number of partition of S in which n plus 1 is in the set of size k plus 1 is this. So this is the number of way we can choose that A1, and this is the partition of this. So therefore, this is the total number. But k is not fixed, k varies, right? K varies from 0 to n. So therefore, by adding all possible values of k, we have Bn plus 1 equal to this. Right? Now what we'll do, we just right. So since we know that n choose k is same as n choose n minus k, So we can write that here since this, right? Now just replace n minus k by k. Or you can say that we just add back from the backward and then you will get this. Or in other words, you can say that n minus k is replaced by k. So you will get this. So this is just a counting argument. So that is the part of combinatorics. So in this way you can prove this. So remember that this is not a part of theorem. You can treat this as a problem because yeah, during exam or we might ask you during combinatorics exam. So this kind of uh, problems actually. So how to count. So we can ask this kind of formulation. Okay, so you have to be familiar with this kind of counting arguments because combinatorics is totally about the counting arguments only. So here we will find all the counting arguments. So we will see this one. This is the trivial counting arguments by using permutation combination. Then we will see some by using some generating function. Okay. And last one, this is the binomial theorem. Now again, by using induction, you can prove it. Now this proof is again very simple, just the counting arguments. So have you seen the proof of this binomial theorem by using induction? Have you seen this before? Anyway, you can use this by the mathematical induction. So first of all, if you take n equal to 0, say, even 0 or n equal to 1, then that is trivial, right? So for n equal, if you take n equal to 0, then both sides become 1. So it is true. Or if you prove that n equal to 1, then also you can find both sides are equal and both sides will be x plus y. Okay. So now this base case is fine. Now we go to the inductive case. So first we assume that this inequality holds for say n. So that's mean this. Or in terms of summation, we can write in terms of this one. Okay. And now we want to prove for n plus 1. Okay. So we shall prove it for n plus 1. Now what we will do? So take x plus y power n plus 1. Now we can write this as in this way. So this just we take x plus y into x plus y power n and then just split it. Right? Now since that x plus y power n by the induction we know the values of this and values of this. Now just put both the values. So we get this one. Right? So we get this. Now we have this multiply with x and we have this multiply with y. Just multiply x and here multiply y. So here we get n plus k plus 1, sorry, n minus k plus 1, and here we get power of y is y power k plus 1. We get this. Okay. Now what we'll do? So this will imply actually. So remember that what was the x y power n plus 1, what we needed to prove. The first term is x power n plus 1, right? And there will be some n plus 1 choose k, this kind of thing. So there we will use that previous one which we have seen. Where it is. Okay, anyway. So we will use that combinatorics argument. Right. So what we will do first, we will first split this one. So we take k equal to 0, then it will be n power x power n plus 1. Then we write it is as 1 instead of 0 to n, we write 1 to n and we will get this one. And here we write k equal to 0 to n and take k equal to n outside. That's mean y power n plus 1. this. Now what we are planning to do, take summation of this and this together, but we cannot do it because their summation that they are different. But what we do to make the same summation, just replace here k plus 1 by k. So that's mean that will be y power k and that will be x power n minus k plus 1 and that will be k plus 1. So just replace k by k plus 1 by k, that's mean you just replace k by k minus 1. So just here replace k by k minus 1, just replace k by k minus 1. So this, that will be this, and this summation will be then k equal to 1 to n. Now since we have same coefficient, right? Sorry, same variable. So we just common the coefficient. So take common the coefficient. And we know that that is same as n plus 1 choose k. And this completes the proof. Okay. So that is very simple. So in terms of slide, if we present, then that whole lecture will be finished within 20 minutes. Okay, since there are lots of calculation here, so I use the slide here. Because there is nothing to understand, right? So this is just a calculation and you will understand if we look at that. So is that fine with everyone? Or do you have any doubt during this lecture?
Sir, we can even use a counting argument here, right? I mean,
Yeah, you can use. So what I'm saying, so this is just one of the proof. This is one proof which I get from a book and I just show you. And you can have many different kinds of proof as well. Even if we ask some problem, that is flexible. You can prove in any. So it is up to you. So how will you prove that? Your combinatorics means just counting arguments. So there are many ways of counting. So definitely, and ultimately you will get that answer. That's all. Okay. So any question? Okay. Oh, okay. He answered that one. No, actually, no, not this one. So this is actually you are calculating the probability. So this means this is the possible way of this, and this is the total possibility. 20 choose 100 choose 10. So that's mean this is the probability, and that value of this one will be less than 1 if you calculate that. But total number of ways should not be less than 1, right? So this is a probability. So the value is less than 1. Okay, then we stop here and all the best for the minor. So if you have any question regarding minor, then you should ask.